Hello, AP Chemistry students. This is Mrs. Altman. We are on video number 18, Liquids and Solids, Part 5. This is our last video in Chapter 10. Here are our objectives for today's video. Pause here. So if we haven't done so already by the time that you watch this video, you will in the future make a heating curve in the lab. And the one thing you'll notice is that when you create a heating curve, you start with something that is in the solid phase, and then you heat it until it reaches either its liquid phase or its gas phase, and you measure the changes in temperature over time. One thing that you'll notice is that once you actually reach the melting point, the temperature just lingers and stops and plateaus. And that is because of something called the heat of fusion. So that is the heat or energy that you must add to a solid to cause it to melt when it is already at its melting point. So let's say if in the case of ice, it's gotten to 0 degrees Celsius, but it's still a solid. Therefore, you're going to need to add a tiny bit more heat in order to break those intermolecular forces. That is why melting is considered to be endothermic. Then there's a heat of vaporization, which is very, very similar. So if you have a liquid that is already at its boiling point, so you've got water at 100 degrees Celsius, it's going to need to break those intermolecular forces, and that's why it will stay at 100 degrees Celsius for quite a while before it will go into its vapor phase. Both the heat of fusion and the heat of vaporization are both measured in kilojoules per mole most of the time. Joules per mole would also be applicable. And sometimes you'll even see kilojoules per gram as well, or joules per gram. They can be used as well. And the heat of vaporization is always, to the best of my knowledge, I cannot think of an exception, higher than the heat of fusion, as when you go from the liquid to solid, you're breaking all of the intermolecular forces, whereas when you go from a solid to a liquid, you're breaking fewer intermolecular forces. Pause here, you don't need all the detail in the drawing. All right, so a heating curve is just showing that temperature as a function of heat added, or when we do this in the lab, if we haven't done so already, it's going to be temperature as a function of time. So notice how I've got a nice linear line for when it's just in the solid phase, and then it plateaus. That plateau is because of the heat of fusion. And then I've got a different line for water, but again, it's linear when it's in its liquid phase, and then it plateaus again, this time for a longer period of time. And then notice that I have gas as well. Another thing I want to point out is that their slopes are different from one another. And that is because the specific heat capacity of the solid, liquid, and gas phases of something can be very different from one another. Pause here. All right, so I will work through this with you. So the melting point, it appears to be 0 degrees Celsius. I know that because that is where there is the first plateau. The boiling point appears to be 100 degrees Celsius, so this is very likely to be water. Now the third question, that's where things get interesting. So remember, specific heat capacity is the quantity of heat needed to raise 1 gram of a substance by 1 degree Celsius. So substances with greater heat capacities will absorb more heat before they increase in temp, and they will have lower slopes. So then we want to see what has a lower slope, the solid or the liquid. So if I'm taking a look, the solid rises from -20 to 0, so 20 over the course of 50 seconds, whereas the second one, in that same time period, the liquid rises about 50 degrees Celsius. So the solid has the higher heat capacity. Pause here. Right, I'm going to break down this problem. So there are two parts. So there are two processes. The first is increasing the temperature from -15 degrees Celsius to 0 degrees Celsius. And then the second is overcoming the heat of fusion. And then we're just going to add them together. So to determine that, I've got Q is equal to mCp delta T. So it is 10 grams of ice. Specific heat capacity was given in the problem. And then my overall difference in temperature is 15 degrees Celsius. I'm not really too worried about sign right now. So I've got 633 joules. But then I also have to consider the heat of fusion. So I've got 10 grams of ice. Here, the heat of fusion was given in joules per gram, so that makes things nice and easy. So then I just need to add them together. And then only because of sig figs, I did 4070. I got 4073 out of my calculator. So I needed to add both of those parts together. Here are the additional practice problems for today's video. Thank you so much for watching and have a great night.